Okay, now we're back for Lochivotera. And this one's a bit complicated. I've got some notes, put some accessory videos up. We'll walk through it. Oh shoot, let me close things. Always let me popping up on me. Okay. So we can use Lochivotera in the competition model to look at the interaction of interspecies competition to figure out who's going to win, who's going to lose, or are they going to coexist. So we can use evidence for resource partitioning has been used as an explanation for the patterns of species diversity found in communities. Mathematical models can predict whether or not the outcome of competition results in competitive exclusion, one loser, one winner, or competitive coexistence. They both survive, although at depressed numbers. The carrying capacity is reduced because they have to share resources. So we'll return to our Lochivotera model with a modification to this logistic growth equation. So as a reminder, our change in population over change in time is a function of the population size, the intrinsic rate of increase, and that's normalized or it's in a relationship to the carrying capacity. So the carrying capacity minus the number in the population divided by the carrying capacity. So if carrying capacity is 100 and the population is 100, 100 minus 100 is 0. So 0 times all this is 0. There'd be no change in the population size. So this is exponential growth until we start to reach carrying capacity, right? And then it levels off at carrying capacity. So this is used to explain the population of a single species in the environment as it comes up to that carrying capacity. Now we have competition we need to enter in here. Why does my calendar keep going crazy? Quit. So now we need to add competition as a factor into this equation. So to incorporate the effects of competition, we use competition coefficients that are subtracted to indicate how strong the competitive effect of one species is on the other. We're going to use alpha and beta as our competition coefficients. And so this is a way of effectively altering the carrying capacity. So we'll look at that next. Okay, sorry for the rough transition. I didn't like the way the next equation was displayed, so I redid it. Okay, so on to the competition coefficients. So this is the same equation we had before, the normal Lochivotera, your organism all by itself, if we just ignore this parameter. Right? Intrinsic rate of growth, population of N1 at a given time, carrying capacity minus that current population divided by carrying capacity. All we're doing here is adding a competition term. So you can think of this as if the carrying capacity is 100 and there's, let me try to do the math quickly. If the carrying capacity is 200, there's 100 of these of your population, and then there's 50 of your N2s that have an interaction strength of 2. 2 times 50 is 100, so we would be at carrying capacity of 200 even though there's only 100 organisms in the population. A couple different ways of thinking about this. Okay, one, let's use an example of N1 as coyotes and N2 as wolves. In our population 1, coyotes, and our wolves are both eating the same thing. They're both eating rabbits. But a wolf is twice the competitor a coyote is, meaning that, say, a coyote eats 1 rabbit every day, and a wolf eats 2 rabbits every day. So in that case, the interaction, the competition coefficient, alpha of N2 would be 2. It would be twice the competitor that a wolf is. That a coyote is. So if a coyote eats, population 1 eats 1 rabbit a day, a wolf eats 2 rabbits a day, in terms of carrying capacity, that's based on the number of rabbits. And if we have a carrying capacity of coyotes all alone of 200, we have 100 coyotes in the population, so we're not yet at carrying capacity. However, there's 50 wolves in the population that are each eating 2 rabbits a day, so we have an alpha of 2. In that instance, 2 times 50 is 100, so we take 200 minus 100 minus 100, we'd get to 0. In that instance, we'd have no change in population with time because we'd be at carrying capacity. So all we're doing is adding a competition coefficient to take into consideration that somebody else, another species, is also utilizing these same resources. That's all that's happening, is we're adding a competition coefficient to account for the amount of resources being consumed by another species in that ecosystem. One thing to keep straight here is when we're trying to estimate the population or model the population for our N1 for our population 1, we need to take into account the competition coefficient for population 2, in this case alpha for population 2, and then times the number in population 2. For our population 2, it's the same thing as above, but now we're using beta to represent the competition coefficient for population 1. So in this case, if we had our carrying, if we use the same wolf and 1500, that would work out. Yeah, 50. Yep, that would work out. Okay, let's do that. So in that case, the carrying capacity for wolves for population 2 would be 100 because they're eating 2 rabbits a day. If our population was 50, same as above, minus our beta, our competition coefficient for N1, coyotes are a crappier competitor, so they have a competition coefficient of 0.5. So if we have their same population from above of 100, so we have 0.5 times 100, which would be 50. So if our carrying capacity, in this case for wolves, is 100, we have 50 in the population, and we have 100 coyotes in the population. However, their beta is 0.5. We'd have 100 minus 50 minus 50. We'd be at carrying capacity in that example. So it's one way of thinking about the interaction between these two things. And so keep in mind, alpha is for species 2 and beta is for species 1. And all we're doing is taking in consideration that something else is consuming whatever item. In this case, we're talking about prey as in like animals, but we could do the same thing for light, nutrients, things like that. That any other limited resource we can use Lacovotera competition model for. It might be a little easier to think of it as like critters eating bunnies, because that's a little more visual. So now we can say that when the change in population over time is 0, the population of species 1 does not change when the carrying capacity, when the population equals carrying capacity minus the competition coefficient for species 2. And a population size in species 2 does not change when the population of species 2 equals the carrying capacity for that species minus the competition coefficient times the population of 1. So let's go back to that and think about that. Let's go back to this equation. So all that's saying is that when carrying capacity, let's go back here, carrying capacity. Yeah. So all that's saying is that if this minus this equals this, then we're there's no more change in the population. Effectively, you can think about this as a more simplistic way of thinking about how species 2 is impacting the population of species 1, meaning species 1 is not able to reach full carrying capacity because you have to account for the amount of the limiting resource that species 2 is consuming. So in effect, what this is doing is reducing K. It's reducing the carrying capacity for species 1 because it's no longer able to exclusively utilize the limiting resource. In the wolf and coyote example, it's no longer able to exclusively eat all of the bunnies. Now the wolves are here and they're eating some of the bunnies too. So it's effectively reducing the carrying capacity for population 1. It's just a way of thinking about how we're partitioning a limiting resource. And so we're going to go through some graphs, and then I'll slow down and break down the calculations for those. So the zero population growth line, or isocline, we talked about this, I think, in chapter 12, if I recall. The zero population growth line, or isocline. So the population does not increase or decrease in size for any combination of N1 and N2, population 1 and population 2. That lies along these lines. So it's a zero population growth. Zero growth isoclines can determine the conditions under which species will increase or decrease. We're going to look at this graph, and then we're going to solve it, and then come back and look at it again. So what this is saying is if we plot population 1, coyotes and wolves on this graph, if we're up here, if we have more of population 1 than the carrying capacity, we're going to decrease population 1 until it becomes along this isocline, this line of zero population growth. Same thing here. If we don't have enough coyotes, or there's not a lot of coyotes, then they'll be able to increase until they get to this level, given this number of wolves. So if we have a lot of wolves, then we'll be up here with fewer coyotes. And so you can think of this as here is carrying capacity 1. This is our 0. So if there's no wolves in the system, coyotes can go to carrying capacity 1. And if there's no coyotes in the population, then the wolves will be at carrying capacity of coyotes divided by the alpha. We'll walk through this, and I'll kind of go back to that example that I made up on the fly, because that would make sense. Because in the example I gave of coyotes having a carrying capacity of 100, and wolves are twice the interactors, they eat twice as many bunnies, their carrying capacity would be, what did I say, 200. I think 200 for coyotes. Their carrying capacity would be 200 divided by 2, which would be 100. Same thing is true over here. This is looking at species 2. So if we're over in this space, we have lots of extra wolves, they'll decline until we get to this isocline. And if we have too few wolves for that given population size of coyotes, we'll increase to here. So here with 0 coyotes, our wolf population will be at carrying capacity. And then the carrying capacity, if there's no wolves in the population, the carrying capacity of coyotes would be K2 divided by beta. In that case, we said our carrying capacity of wolves was 100. Our beta was 0.5, so 100 divided by 0.5 would be 200. So we'll walk through how we determine how we can use that prior equation to mathematically calculate K and K1 divided by alpha. So if we just start with our prior equation of N1 equals K1 minus the competition coefficient for N2, we can solve for it. What happened there? I don't want you. We can solve for a few things here if copying and pasting works for me. Okay, so if we start with, let's start with N2 equals, I gotta bump that back up, equals 0, then we've got N1 equals K1 minus alpha times 0. So that is simply N1 equals K1. That makes sense, right? If there's no competitors in the population, then N1 equals K1. The N1 species does not have to share resources with a competitor. It would be just as if they didn't exist, because they don't. Now let's solve for the K1 over alpha term. So in that case, we have, what did I do here? N1 is 0. So let's do N1 equals 0. Go back to our equation here. So 0 equals K1 minus, sorry, it keeps being loud, minus alpha times N1. We'll add alpha N1 to both sides. Equal to, is that what I did? Equal to, let's get, equal to K1. And we're trying to solve for N2. So we're going to take this, divide it by alpha. So divide alpha over here and divide alpha over here. Oh, it keeps wanting to be small. Stop being small. There it goes. So all we're doing here is solving for N2 to get both our X and Y intercepts. And this makes sense with the example given of a population of K of 200 for coyotes and a K of 100 for wolves, particularly if wolves are twice the competitor that coyotes are. So it's one way. It kind of helped me to think about it this way. And we'll go back here and walk through that. So again, okay, so this makes sense that for population 1, they're at carrying capacity if population 2 is at 0. They're not sharing resources. And then the carrying capacity for 2, effectively, right, is the carrying capacity for species 1 divided by the competition coefficient for species 2. So it's a way of thinking about almost like, I guess hungry hippos is a bad analogy, but maybe the 2-to-1 analogy of eating bunnies, I think, makes sense. So it's mathematically how we derive that. So hopefully that gives us a solid background to go through the next one, which gets more complicated, where we're plotting both of those isoclines together and seeing how they interact. So this graphical approach can be used to predict the end result of competition. N1 and N2 isoclines are plotted together for 4 possible combinations. When the isoclines do not cross A and B, competitive exclusion results. Okay, we'll look at that. Competitive exclusion meaning somebody survives, somebody doesn't. So one of the species survives, the other one doesn't. Depending on which isocline is above the other, either species 1 or species 2 always drives the other to extinction. So when we look at the isoclines, you want to be the top isocline. So here is one example of this graph. We've got the species 1 isocline here. So for N1, for species 1, the x-intercept is K1, right? The carrying capacity if no species 2 are there. And then the carrying capacity here, or the intercept here, is K1 divided by alpha. Here's species 2, the carrying capacity if no species 1 is there. And then here's the x-intercept for species 2, which is K2 divided by beta. If we're up here in the blue, this is going to drive the population towards this isocline. It's going to decrease both the number of species 2 and 1, resulting in a net decline for both of them. if we're down here in this section, we're below the lines for both of these, and so it's going to drive an increase in species 2 and an increase in species 1. If we wind up in this space, we're above the line here, so it's going to drive a decline in this population, which is going to ultimately increase this population. So it's going to drive down population 2 and increase population 1 is increasing in this direction. So this is increasing population, even though it's pointing down. Think about what's down here. This is the population level for population 1. So as things move further down, point this way, we're pointing towards an increase in population 1 and a decrease in population 2. So ultimately the interaction will result in population 2 moving towards 0. And so here, so depending on the population size and where they are in this graph, ultimately it results in a stable equilibrium at K1. So ultimately species 2 will lose out in this example. Same thing is true here, with the exception now species 2 has a higher isocline. So for N2, we've got carrying capacity for 2 divided by the carrying capacity of 2 over the competition coefficient. And species 1, with the carrying capacity of species 1 divided by the carrying capacity for species 1 divided by the competition coefficient for species 2. Up here in the blue, it's driving both of these down, so overpopulation. Down here, generally underpopulation, is driving an increase in species 1 and species 2. If we wind up in between, this is going to do effectively the opposite of the prior one. Just the arrows pointing in different directions. That's really the only difference. But if we wind up in here, this is decreasing population 1. So we're above the isocline for population 1. So just if you ignore this line right now, ignore the population 2 line. If we're just right here looking at the isocline for K1, you'd predict a decline, right? But we're below, and if you ignore that isocline and we just look at the isocline for N2, and we're right here, that's going to be an increase. So we're in this zone where we're overpopulated for population 1 and underpopulated for population 2. So that will result in the population bouncing around and eventually, or moving around, and eventually stabilizing at carrying capacity for species 2. So in that case, species 2 would be the winner at the cost of species 1. So we'd wind up being at carrying capacity for species 2 and species 1 being at 0. These next graphs, this is the text for the next graphs. Maybe we'll look at this one at a time. So in the next graph, competitive exclusion occurs, but which species wins depends on how densities change over time. I might copy that and look at this one. So put this over here. So see, competitive exclusion occurs, but which species wins depends on how densities change over time. So here we've got a bunch of different factors happening here. Let me take a look. Okay, so now we've got two different isoclines plotted on the same graph. We can look at our population 1 and our population 2. If we wind up in the blue area, both populations decline. If we wind up in the, I don't know what that is, beige area, both populations are increasing. If we wind up in either of these shaded areas, that'll determine who wins. And so if we wind up in this space here, this would be below the isocline for species 1, which is plotted here, K1 through K1 divided by alpha. So we wind up here, it's below the isocline for species 1, so species 1 will increase, go this way. That's above the isocline for species 2, which is plotted here, K2 divided by beta over K2. So you can think of that as above the isocline for species 2. So there's too many species 2, not enough species 1. Then decline species 2, increase species 1, resulting in a stabilization of K1. So we'd have competitive exclusion in this example. Over here, if we're in this space, we're above the isocline for species 1 and below the isocline for species 2. So in this example, we're above the isocline for species 1. So species 1 is going to decrease and species 2 is going to increase, resulting in a net movement to a stable equilibrium at K2. In this case, species 2 would win the competitive exclusion fight, and then species 1 would go extinct. Let me copy the text from this and drop it on number D here. There we go. Okay. So now here we have a slightly different interaction. So here we are able to come up to a happy medium where we've got our isocline for species 1 and our isocline for species 2. So if we're in this space, we're overabundance for both of them. It's going to lead to a decline. If we're in this space, we're under our isocline for both of them, which is going to lead to a decline. In this space, we're over here, we're over species 1 and we're below species 2, so it's going to lead to a decrease in species 1 and increase of species 2, resulting in hitting this equilibrium here. And if we're in this space, we're over for species 2, so we'll decline species 2, and we're under for species 1, which will result in an equilibrium here. So only when you've got this interaction where no matter where you are in the graph, it's leading to this equilibrium, you can have a stable equilibrium where both species are coexisting. So we can have coexisting coexistence here. On the other combinations, we're having competitive exclusion. So again, in this model, at this point, we're able to have coexistence as opposed to competitive exclusion. So coexistence occurs when alpha, the competition coefficient for species 2, is less than the carrying capacity of 1 divided by the carrying capacity of species 2, which is less than 1 divided by beta, the competition coefficient for species 1. So if alpha and beta are equal or close to 1, the species are equally strong competitors and have similar effects on one another. So there's not a big imbalance in their competitive strength. So in this example, if alpha and beta are both 0.95, so you have 0.95, which is smaller than K1 divided by K2, so if they have similar carrying capacities, and that is less than 1 divided by beta, which would be 1.053, then coexistence is predicted when the two species have a similar carrying capacity. So if they're both carrying capacities of 100, then this would be 1. And 0.95 is less than 1, which is less than 1.053. If alpha and beta are both equal to 0.1, coexistence is predicted with a much broader range of carrying capacities, meaning that, so here we've got alpha, 0.1, 1 divided by beta, which is 10. So now we can have carrying capacities ranging, a ratio of carrying capacities ranging from 0.1 to 10 and still reach coexistence. So if we had a carrying capacity of species 1 of 100 and species 2 of 200, that'd be 0.5. We're still in between those. If we have a carrying capacity here of, I want something just under 10, of 100 divided by a carrying capacity of 15, that would still be less than 10. And so it gives us a much wider range of carrying capacities because their impact on one another is a fair amount less. And so this gives us a broader range of carrying capacities that can be supported under coexistence. Okay, I know that one's a lot. Go back and kind of like read through the chapter, and I put a link or two up to look at some other ways of explaining it. But really kind of start with the first principles of thinking about the isocline, like what does this mean, as well as really what we're talking about here is the competition coefficient impacting the carrying, basically related as it relates to the carrying capacity of the species. And so just think of this as an interaction term that's effectively reducing the carrying capacity for that species because we're competing for resources, right? The whole thing is about competition. So hopefully that helps. We've got one more section here to wrap up the last little bit, but we're almost there.